Hello, everybody, and welcome again to Physics Rich, your one-stop channel for the preparation of IIT-JEE Mains, Advanced, NEET, and also AP. Guys, today we are doing collisions, and I'm going to teach you a very beautiful problem in collisions. This is the Awesomeologist series directed towards mastering your concept application in collisions. So, guys, let's look at the problem. Here you can see a beautiful imagery of two balls colliding with each other, and this is the problem. So we have a rigid massless rod of length L. Here you can see the rod of length L, and it joins two particles of mass m each. They have m each, as in like this mass and this mass. They are both m. Now this rod is lying on a frictionless table. You see this entire thing is a frictionless table. And it also says that there is another particle A of mass m. It's an identical particle of mass m. And identical as in it is identical to both of these. So we can write over here that this has a mass m, this also has a mass m, and this also has a mass m. All three of them have mass m. And this collides with the ball B. This is a rigid massless rod, so obviously as it collides with ball B, there will be some effect on ball C also. So now there are a bunch of questions that are asked over here. You have to find the final velocity of particle A, as in like after collision, what will be the velocity of particle A. You also have to find the angular velocity of the rod, velocity of center of mass of B and C. The center of mass of B and C will lie at the center, so we have to find the velocity of this particular point. And we also have to find the impulse on the ball C. And obviously the impulse on ball C will be because of this rod itself. Okay, so this is the question. Now let's take a look at the approach of this problem. You see, guys, that there are actually two approaches to this beautiful problem. We can solve it using the energy method, and we can also solve it using the restitution method. I would like to show you the energy method first, because I personally feel that the energy method is actually simpler to understand. See, this ball moves with a velocity of v naught. Yeah, and these two are at rest. All right, there's no friction anywhere. We are going to assume that this thing comes, hits, and goes back. Okay, it comes, point, and then goes back. Okay, or perhaps it doesn't go back. We don't necessarily know if it goes back or if it keeps moving forward. But we can definitely say that this thing will have a velocity of v1. V1, and that will be our answer of the first part. Like this is what we are looking for in the first part. V1 is the final velocity of the mass A. This is the particle A. Okay. Now, let me mark the particle A over here. This is B and this is C. So, first things first. Is the momentum conserved? Yes, the momentum is conserved. Why? There is no net external force acting on this system. I mean, they're all kept on a table, right? But we are not concerned with forces in this direction. We are concerned with forces in this direction. Then you can say that, sir, but isn't it like this guy is going to hit this guy? There will be a force between these two. Yes, there will be. But those forces will be equal and opposite and they will cancel each other. So we are not bothered with that either. But then again, you would say that, sir, but didn't you teach us that you should draw FBD of only one object? Here, A will be applying force on B, B will be applying force on A. These are forces acting on two different bodies. How are you saying that they will cancel each other? You taught us in the previous lectures that you should always consider FBD of one body and only count forces on that body. So, my dear students, the answer to that is, if I consider this whole thing as one system, then the A and B interaction force will become an internal force. That's why I don't have to worry about it. In fact, you know what's going to happen? This B and C will also have some sort of interaction. Actually, this B will apply force on the rod will apply force on the B. And because of that, the force will transfer over here and it will apply on C. But then again, B on rod, rod on B, cancel. Rod on C, C on rod, cancel. So there is no net external force on the system. We have established that. And because that there is no external force in the system, you can easily conserve linear momentum. So you can write that conservation of linear momentum, conservation of linear momentum will lead to one very nice equation, and that will be mv1, which is the mv naught, I'm sorry, not mv1, mv naught, which is the initial momentum of this particle, should be equal to final momentum of this particle mv1, okay, and also the linear momentum of this whole system. Now, linear momentum of two particles together can be written as their total mass times the velocity of their center of mass. Okay, velocity of the center of mass BC. And in fact, guys, in one of the questions, we are required to find the velocity of the center of mass of B and C. Okay, so we can write this equation, and you can see that m is a common term, so I can simply write V naught equals to V1 plus 2BC. Now, this is my first equation. This is a very important equation. Okay, see, why am I saying that this is a very important equation? Because it is coming out of one important physics concept, which is conservation of linear momentum. Okay, you will find in physics that all the equations that we get are due to one or the other conservation laws or kinematics or Newton's laws. Okay, like they all revolve around some physics concept. An equation come out of one physics concept. You should be very aware of what concept you are applying. We have applied linear momentum. Now, secondly, what other concept can you apply? We can also apply conservation of angular momentum. Let me just write the conservation of angular momentum. Now, you should be asking me a question over here. Sir, didn't you teach us that the moment you say angular momentum, you should also specify angular momentum about which point? Yes, of course. I have always taught you that if you talk about the word angular momentum, mention about which point. So which point am I going to choose? So here's the thing, guys, because all the forces in this entire system are internal, and internal forces never really have torques, so we can conserve the angular momentum about any point. Here, I have seen in my personal experience that students really enjoy going to the center of mass of this system, and they try to conserve angular momentum about this point, which is the center of mass of this B and C. This way, they try to avoid using perhaps the total linear moment, total angular momentum situation for this rod. But in my personal opinion, as a teacher and in fact as a student, I would tell you that you should conserve the angular momentum about this point. So we will conserve the angular momentum about the point B. Okay, about the mass B. Now, this is particularly simpler compared to this point because of one simple reason. There is no angular momentum of this guy about B. You know why? Why? Because what is angular momentum? Angular momentum is given as R cross P, right? R cross P, where P is the linear momentum. Now see, the linear momentum of this guy is pointing towards B. R vector cross P vector. R will be what? Going from B to this. Okay, so this would be R vector, and this would be the linear momentum vector. You see that these two vectors will be anti-parallel. Okay, so this comes out to be RP sine 180 in our case. So we don't have to write that. What is sine 180? It's 0. Okay, you have to know that. It's so this angular momentum is going to be 0. Also, one more thing, one more very important thing, that when this collides with the mass B, you can see that the impulse will be in this direction itself. So on A, the impulse will act over here, and on the B, impulse will act over here. So the impulse also is in the same direction. So we can say that the angular momentum of this ball before and after are both 0. Okay. So if I say that the sum of all angular momenta of the entire system, sigma Li, equals to sigma LF, and I'm only talking about the point B, then I can say that the Li value for wall A plus Li value of this rod of this system, we'll call it CB, okay, should be equal to LF value of A plus LF value of CB. I hope you are able to understand what I'm writing. Li means the initial angular momentum of A. Okay. LF means the final angular momentum of A. Li means the initial angular momentum. LICB means the initial angular momentum of the CB system. And LF is the final angular momentum of the CB system. Now, what I'm trying to tell you guys is that there are three of these are zero. This is zero. This is zero. And guess what? This is not moving. So this is also zero. Okay. You understand? So these three terms are zero. So can I consolidate this? Of course, I can consolidate this and I can write that the angular momentum, or perhaps I should copy this over here. The angular momentum of this finally is zero. So how can I write the angular momentum of this rod about the point B? Now this is where the formula for angular momentum comes in play. L is given as angular momentum about the center of mass. We also call it the intrinsic angular momentum. Intrinsic angular momentum as in like because the whole system will tend to rotate about its own center of mass. So that will be its intrinsic angular momentum plus R cross total mass over here will be 2m VC. Where what is R? R vector, guys, R vector is going to be this vector. This is going to be R vector. And remember that this length is L, so this will be L upon 2. Okay, and also remember that this angle was given to us in the question. The angle was 45 degrees, so we will choose this to be 45 degrees. Okay, so we understand that this is the final angular momentum. Okay, we are only looking after this term. So the final angular momentum is supposed to be found out, and this is zero. This whole thing is actually zero. Okay, so what is the LCM? LCM is the angular momentum of this system because of its rotation. So think about it this way, guys. This guy comes, hits, and you will start to see it rotating about the center of mass. And when something rotates, it has omega. Okay, and about the center, you can write I, which is the moment of inertia, times omega. Okay, so we will assume that this is beginning to rotate like I, omega will be its angular momentum. Omega will be its angular velocity. Now plus, we will do plus R. R vector is this L by 2. Okay, L by 2 times mass will be 2m. Okay, and then there will be VC. VC is in this direction. This direction is VC. VC. Okay, but the angle, what is R cross VC? Be sin 45. So we will write a sin 45 over here. R cross VC. But you see, guys, there is one small tiny problem over here. That the omega is counterclockwise. And what is this R cross V? It is clockwise. So instead of writing a plus over here, we should be writing a minus. And that is the whole reason why it will become 0. Okay. Alright. So now what can I write about I though? I, moment of inertia of this whole system. What will it be? About the center of mass, it will be m L by 2 whole square. Like, you know, mr square is the formula, no? Mr square is the formula. So m L by 2 whole square will be the moment of inertia of one of these. And we multiply that with 2, so because there are 2 of these. So this is actually ml square by 2. See, this will be L by 4, as in L square by 4, and then 2 cancels, so ml square by 2. Okay, so let's take it to the next page. So this becomes m L square by 2 omega minus, this 2 will cancel, this 2 will cancel, m VCL sine 45. M VCL sine 45, and that is 0. you can see that I can cancel this M over here and I can cancel this L over here, and I get omega L becomes equals to 2VC sine 45. The 2 will go there in the cross multiplication, and this becomes square root of 2VC. Very important. Okay, so I get VC equals to omega L upon square root of 2. Another very important equation. Where is my first equation? This is my first equation. Okay, V naught equals to V1 plus 2VC. And this is my second equation. But you see that now I have introduced one more variable. I have VC and V1 as my variables. And I have introduced one more variable, which is omega over here. But I have also utilized one more concept of physics, which is conservation of angular momentum. So I have three variables, V1, VC, and omega. Okay. Now the thing is, we need a third concept. And what is our third concept? So guys, if you read the question again very carefully, you will realize that it is written that identical particle A of mass moving with velocity V naught collides elastically. Okay, please do not forget that it is written that the collision is elastic. And what is the meaning of elastic collision? The meaning of elastic collision is that energy is conserved. So like I said, that I will solve this problem for you using energy conservation. So I will now write the equation for energy conservation. We will squeeze this onto one side, and then we will write conservation of mechanical energy. You see, guys, there is no necessity of writing the conservation for mechanical energy and include potential energy in this problem, because there is no such potential energy issue going on. The only issue is of kinetic energy. So the kinetic energy is conserved. Initial and final values are equal. All right. So what is the initial kinetic energy? Is it half mv naught square? Yes, sir. Definitely, sir. It is half mv naught square. And later on, what is happening? Later on, you see it collides and then it starts to move with the velocity v1. So finally, it has a kinetic energy of half m v1 square. But that is not the end of the story. There is the kinetic energy of the rod also. Okay, the rod, this rod also. Now it is see rotating. It is rotating, and also the center of mass is translating. So guys, for those of you who know how to write the kinetic energy of a rotating rod, it's great. You can simply write the kinetic energy of rotation plus the kinetic energy of translation for the rod. Okay, you can easily write it this way. And for those of you who don't know, this is the time you should learn that a rotating rod will have two kinetic energies. Actually, it will have one kinetic energy, but we understand it that way, that it has two kinetic energies, one due to rotation about the center of mass and one due to translation of the center of mass. So how do we write this term? See, kinetic energy of rotation is simply given as half I omega square. What have we found out I to be? We have found out I to be ml square by 2. So there is a 2 over here, and that's why it will become a 4. And that's why this becomes ml square omega square by 4. And then what will be the kinetic energy of translation? You see that the center of mass is moving with a velocity of vc. All right. That's why the total kinetic energy will be half into 2m into vc square. Now our job is to put it over here. But you see, guys, that I have already found a very nice relation over here. Vc equals to omega L upon root 2. So from here, can I say that Vc square will be equal to omega square L square upon 2? Of course, I can say that. So I can actually take this and put it over here, and it will actually solve my life and make it a lot better. It will become omega square L square by 2. So this becomes m omega square L square by 8. And what is this? This is just simply m Vc square. Sorry, this is not omega square L square. In fact, I had to substitute omega square L square. No? So it will become 2 Vc square. Pardon me over here. So omega square L square is going to be 2 Vc square. So this becomes m Vc square upon 2. Okay. This omega square L square is going to become 2 Vc square. So I'll just put a 2 Vc square over here. So the 2 and 4 will cancel. It becomes 2. So now, what do I have? What do I have now? See, let's consolidate this equation. I have half m v naught square equals to half m v1 square plus. What is my kinetic energy of rotation? mvc square by 2. And what is this my kinetic energy of translation? mvc square simply. Correct? So I see that there is a 2, 2, 2 over here. Why don't I make a 2 over here and 2 over here as well, so that I can cancel all of these 2's, and I can also cancel all of these m's. So I just simply get v naught square equals to v1 square plus vc square plus 2vc square. Oh wow, this seems to be becoming simpler. So this is becoming 3vc square, and this is my equation number 3. You guys remember what was our equation number 1? This was our equation number 1. V naught equals to V1 plus 2Vc. V naught equals to V1 plus 2Vc. This was our equation number 1. So now we have simply got two equations and two variables, which we can very easily solve. All right. Now, shall we solve it? So let's solve this thing. And two of our answers should come right from here. So how do we go about it? What do you want to find first, V1 or Vc? I think it's easier to simply substitute V1 itself. In like from 1, we will substitute V1 in 3. So you get V naught square equals to. Now what can I write from here? I can write V1 is equals to V naught minus 2Vc. We'll put that over here. So I get V naught minus 2Vc square plus 3Vc square. Okay. Okay, let's continue. So this becomes V naught square equals to V naught square plus A minus B whole square. 4Vc square minus 4 V naught Vc plus 3 Vc square. I see a lot of cancelling happening. So there's a 0. Now this remaining term becomes equals to 0. So I can just copy this and put this equal to 0. Is that actually a quadratic? I don't see that this is a quadratic. I see that this is a 7 Vc square, and this is equals to 4 V naught Vc. In fact, Vc cannot be equal to 0, so I find that equation to be giving me a trivial solution, which means that my answer for Vc is 4 V naught by 7. Okay, 4 V naught by 7. And what is my V1? The V1 value that I need to find is V naught minus 2 Vc, and that will be V naught minus 2 times of 4 V naught by 7, which is actually V naught minus 8 V naught by 7, and that will come out to be minus V naught by 7. You see that? So I am getting a negative value. What does it mean? It means that the ball after colliding must be going backwards. So guys, I think we have successfully found out the final velocity of particle A, and that my answer is coming out to be equal to minus V naught by 7, and center of mass is moving with 4 V naught by 7. In fact, I have also found the angular velocity of the rod, because I have this relation over here. I have this relation, Vc equals to omega L upon root 2. So from here I can say that omega will be root 2 Vc by L. I have found out the value of root Vc as 4 V naught by 7. So my omega is 4 root 2 V naught by 7 L. Okay, so let's put that in the answers. So this is also something that I found out, which is 4 by 7 root 2 V naught by L. Now impulse on C is all that I need to find. All that I need to find is what is the impulse on C. Okay, let's check out the impulse on C. Now this is a very interesting take on this problem. See that this is the ball C, okay, and well, this is the ball V. We now know that the velocity of the center of mass is going to be equal to 4 V naught by 7. Okay. And we also know that the angular velocity is omega equals to 4 root 2 by 7 V naught by L. All this information is with us. All right. What exactly are we looking for? We are looking for impulse on C. Impulse on C. My dear students, very importantly, that C must be getting a force along the road. Okay, which means that the velocity that it must have gained must be over here, and that should be the velocity of C. However, you see, what is the change in momentum for this particle C? It will be mv. Okay, let's call this v as v dash. I don't want to call it vc because c is the center of mass. Delta v is mv dash, and that itself is our answer, mv dash, which is I. That is the impulse on C. That's what we are looking for. But how do we calculate the velocity of C? How do we calculate this v dash? So for that, guys, you need to understand the kinematic relation. That velocity of the point C, or rather I should say, velocity of the point C with respect to the center of mass is given as the velocity of the point C, which is v dash, minus the velocity of the center of mass. Okay, these are all vectors. Now, what is my v dash? V dash is what I'm looking for, and that is actually velocity of the center of mass plus the velocity of the this object C with respect to the center of mass. Okay. Now, it's become a little confusing because of the nomenclature. The point itself is also C, and the velocity of center of mass is also C. So you know what we should do? We should actually start calling this as VCM. VCM is equals to 4 V naught by 7. We should start calling it as VCM. All right. And this is VCM. Now it's fine. So velocity of this point will be the velocity of center of mass plus its velocity in the frame of center of mass. So in the frame of center of mass, guys, it is having a velocity vector in this direction, which is here. Okay, and you know what this will be? This will be L by 2 omega. And also it will have a velocity in this direction, which will be 4 V naught by 7. So now I'm supposed to add these two vectors, okay, such that this angle is going to be, well, 90 degrees, okay, and this angle is going to be, well, 45 degrees. All right. But the thing is that we know that the velocity is only in this direction. Okay, I mean, check out the vector velocity diagram. So this is a VC. Okay, this is VC. VCM, sorry, VCM. This is the direction of V dash. This is what we're looking for. And we have another velocity over here, which is L by 2 omega. And we know that the resultant of these two has to be over here. And this angle is 90 degrees. My dear students, I already know that this is 45 degrees. Okay. What it means is that this L by 2 omega is not going to have any component over here. So all I need to find is VCM cos 45. That's it. That's it. I mean, problem over. Okay. This is the problem. And we are doing it because the component of L by 2 omega over here is not going to exist. The component of VCM over here will be VCM cos 45, and that will be simply M. Now what was VCM? VCM was 4 V naught by 7. So we will have 4 M V naught by root 2, 7 root 2. That's our answer. 4 M V naught upon 7 root 2. Okay. So yes, we have come to 4 M V naught upon 7 root 2. Alright guys, so that concludes our solution. So I hope you enjoyed this solution guys. I will tell you the next approach, the second approach in the next video. So stay tuned and until then, stay physics rich.